something means that something is wrong, and if we use that model in a different way to predict surface temperature against albedo, then we can show for the Earth that the Earth should lie along this line here, and it lies above the line up here. So something's missing. Our simple model, our two-element model, is not enough to do it. So our model is not wrong, it's just not taking everything into account. So we've got to add a little bit to the complexity of the model. So we postulate a new model, and the way we postulated that is to say that we have an atmosphere. The previous model said nothing about the nature of the atmosphere at all. A uniform atmosphere of sort of inert atmosphere, this is what would happen. So we say, no, let's have an atmosphere and let's bung in on that atmosphere something that does something to long-wave radiation. So we have an atmosphere and we separate it from the Earth. Basic first part of the model comes in, there's the sunlight coming in, shortwave radiation, bam, bam, bam. And that was our simple model, that's all we had previously. Sunlight in, sunlight out, albedo of the Earth's surface, warming taking place. We now add another parameter, and we say, right, that warming hits the atmosphere. This atmosphere has certain characteristics which lead to it warming by greenhouse gases, particularly CO2, that intercepts the outgoing long-wave radiation. Some of it retains into here, some of it still loses from the system as radiation. So it's slightly complicated. And if we apply that model by saying, right, now we're just putting this extra bit in the model about long-wave radiation, all that's emitted from the Earth's absorbed by the atmosphere, re-emitted all over in equal directions. How does that affect then our model? The expected relationship between albedo and surface temperature, assuming radiation input is constant, allows us to just about hit the line. So this was the simple without greenhouse gases relationship. This is the one with greenhouse gas relationship. It's almost there. It's not totally there. It's still not explaining everything. But at the moment, for the total albedo of the Earth around here, this is what we'd expect the temperature to be. It's about right. So it's still a very simple model, but it's just added another bit to it. It's sort of, and the idea behind models is that you effectively add bits and bits and bits to try and improve the prediction from the model or the projection from the model to the reality of what you observe. Now that's what all modelling is about. So our energy balanced greenhouse gas model is really very good. It's not totally good, it's somewhere thereabouts. Why would we want to add to it? What processes are missing? And if we think about that, we can think, right, we've got some real complications. There's no dynamism. This is a snapshot model of one simple time period. So there's no time varying components. It's not dynamic, it's static. And we know that we have time varying components which will lead to feedbacks, positive, especially negative feedbacks. We also know that that simple model doesn't have any spatial variability, so it doesn't have a tilting Earth, it doesn't have variations in radiation input with latitude, etc. So it's a gross simplification. The interesting thing is it's still almost correct. It still almost gives us the number that we need, despite the fact that we know that it doesn't include all this complication. And this sort of harks back to predictions of greenhouse gas warming for doubling of CO2. Arrhenius, back in the late 19th century, predicted on the back of an envelope that if you double CO2 in the atmosphere, global mean temperature would rise by about 2.5 degrees centigrade-ish. All our models, the more complicated we get, still seem to focus down on that as a basic number. So the question is, do we really need all these models if Arrhenius was right on the back of an envelope with a simple energy balance model? And we've got to the stage with modelling now where people are beginning to question the need for ever-increasing complex models if the fundamental knowledge that's coming out really isn't that much different. Actually, one or two simple things drive the model, therefore why do we need that at all? So we know, for instance, that the reality of the Earth is this. This is solar radiation coming into the Earth through time and across latitude. So it's not a simple system. But we can, with very simple modelling, get it almost around the right sort of figure that we need to do, despite the fact we know that the complexity is like this. So that sort of basic idea is how we structure models. We have confidence that if we can simplify reality into the key components and find some way to move into a dynamic form, then basically we've got a method, an approach which can give us the way in to producing simple models that will be able to project into how the system operates. And so what we need is to accept that it's dynamic, which is to move energy and matter from one place to another. We need to be able to, the way we do that is to divide the Earth into boxes. So you all get into your little boxes. You have little boxes of atmosphere, you have little boxes of ocean, and effectively you move from one box into another box. Each box has a characteristic, and then one box feeds into another box. Very simple ones, sometimes called these zero-box models. Here's a simple two-box model. All the world is a box. Two boxes, 1 and 2. Energy can enter and leave in any direction. It can flow from box to box. It's fairly open. It depends what it wants to do. It's a very open energy system. Matter has to be constant and can only flow between boxes, but has to stay overall as the same amount of box. So it has to move from one box to another. It can't move in all directions. And so, let's say we have boxes 1 and 2. Let's say box 1 is stimulated by solar radiation. It has an input coming across into the box. Then we predict, or rather project, what happens between box 1 and box 2. So effectively, box 1 warms. So the energy is used to warm box 1. And we know that energy can move out of that box in any direction, so we would say, right, if we have this amount of energy coming into box 1, then energy is lost in this direction, or moves in this direction, but also moves into box 2 to warm box 2. So it's an if, then. So if that happens there, then that happens into 2. And obviously, if you then have other boxes, that will trigger box that way, and the energy moving this way, we can begin to build boxes up and down this way. And so we move effectively from one box to another. And we can see how that movement can be simplified. We've got the processes by which that happens. Shortwave radiation, long-wave radiation, advection, horizontal movement of energy. And those are physical processes which we can put numbers on. Those are physical processes that we can predict how we expect them to behave. We can predict how we expect advection to take place. We can put numbers on. We can put a number on how much shortwave radiation coming in. We can predict, therefore, how much we might expect to be emitted as long-wave radiation. It's a black box. The Earth is a black box, for instance. And then we can say, right, that's a simple one. Let's go out and measure. Let's go and put a box round in the atmosphere and let's just measure these and see if our predictions actually work. So it's basically, we can do that with energy. And we know that the amount of heating in box 2 is fundamentally controlled by advection. So if warm air is advected, energy is advected, then box 2 will take the energy from box 1 and warm up more. if not very much is advected, or the effect is not an effective process, the energy will stay in box 1 and will not therefore move into box 2. Oops. So, if the process of advection really isn't affecting very much, there'll be minor warming here and most of the energy will be used in this box. And you can assume that depending on, if we complicate this by putting it onto the globe, then different parts of the globe, advection will be stronger or weaker, and therefore we can estimate. And we can then say, right, why should this be the case? Well, let's have a look at the other parameters, and we begin to build up the complexity of parameters. If the yellow arrow was always the same magnitude in the same place, the whole system would just stay constant. But that's the bummer, it's not. The Earth is tilted, so the position of the yellow arrow, so the position of this changes through time. Like today, it's pretty low off, it's pretty incidental heat coming in. As we move towards the summer, if we could see the sun, we know that we would get more direct, we would get more concentrated energy, we would get more shortwave radiation coming in. So we have to realise that as that moves through time, then the whole system is in a different sort of balance. What happens to matter? If volume and temperature are the same, you've got different matter in box 1 and box 2, you can move matter from box 1 to box 2, and you might expect that as matter moves, if we've got so we can predict the amount of matter that's going to move. If we then heat box 1 and assume that we've got an equal amount of matter between box 1 and box 2, we shift matter, we stimulate that matter, and that will move into box 2. So we can again move material from one box to another. So the whole idea behind modelling the Earth, whether it's the atmosphere or whether it's the ocean, is simply to